All right, in this example, we're going to put everything together and we're going to graph a function using calculus. All right, so we're given this function f of x equals 5x e to the minus x. Okay, and I've kind of broken it down step by step what we're going to do here. The first task is just to find the coordinates of all the x and y intercepts. So remember that the x-intercepts occur when y equals 0, right? So I'll say y equals 0 gives you the x-intercepts, and when we set x equal to 0, then we get the y-intercepts, right? Because everywhere on the x-axis, y is 0, and every point on the y-axis, x is 0. All right, now I can let's start with the first one. Let's set this 5x e to the minus x equal to 0, right? That's when y is 0. Now, the important thing to recognize here is that we have two factors. We have 5x times e to the minus x, and e to the minus x is never 0, right? If I graph e to the minus x, what does it look like? E to the minus x is exponential decay, and so it looks like that. Right? It's never 0 and it's never negative, right? So the only factor that could cause this to be 0 is the 5x. So this whole thing is 0 when 5x is 0, which means that x has to be 0. All right, so the x-intercept is 0, 0. Right? Now the y-intercept, that's kind of given us the y-intercept as well because, you know, obviously when x is 0, y is 0. But if we do f of 0, right, that's normally how we would find the y-intercept. If we just put in x equals 0, and you get 5 times 0, and then e to the 0. Right? Now, anything times 0 is 0, so you get 0. So in this particular function, the x and the y-intercepts are the same, right? It just passes through the origin at 0, 0. All right, now the next question is asking us to find the x-y coordinates of the critical points, okay? And use the first derivative test to find the values of any local minima, maxima. All right, so find the critical points. So we need the first derivative. Okay, now I've scrolled up to, maybe I should just keep this scrolled down a little bit so we can see the function at least for now. We're going to take the derivative of this function. Now notice again, we have a product. We have a product 5x times e to the minus x, right? It's really 5 times x times e to the minus x, but I'm going to treat 5x as the first function, and then that is multiplied by e to the minus x. So I need the product rule. I need to use the product rule on this one. So if I treat the first function to be 5x, the derivative of that is just 5. So I take the derivative of the first times the second, and then plus the first times the derivative of the second. So the derivative of e to the minus x, you can treat it like, you could use the chain rule on it, or just recognize that we can bring down that constant of -1, right? All right, so that's not very clean right now. I could have made this plus into a minus because of the -1, but let's clean this up because we have to set this equal to 0 and solve for x. So I think what I'm going to do first, I see that I have a common factor of 5, and I also have a common factor of e to the minus x, right? I just have two terms, and both of them have a 5 and an e to the minus x in it. So if I factor that out, what I'm going to have is 1, right? When I factor e to the minus 5x, sorry, 5 e to the minus x out of 5 e to the minus x, and just get 1. And then over here, I'm going to be left with x times a -1, which is just going to be minus x. All right. Now you can see that's a lot easier when I set it equal to 0 to figure out the critical points, right? Now again, e to the minus x is never 0. So this 5e to the minus x is never 0. The only thing that could possibly be 0 is the 1 minus x. So my critical point, I'm going to say critical point at x equals 1. Okay, that's my critical point. So now I just need to test it. So let me go ahead and let's draw a little number line. I'm using the first derivative test on this one. I could use the second derivative test, but you can see this is one where it's actually easier just to use the first derivative test, because if we take the derivative of the derivative here, we would have to again use the product rule again, and which is fine, but it just is not very pretty. So let's just use it. We're told to use the first derivative test, but this one is one where it's probably easier just to use the first derivative test. Okay, so we need to if we're going to use the first derivative test, we have to test points on either side of 1, right? And I have to test the derivative to see whether it's increasing or decreasing. So I'm testing the slope of the function. I'm going to pick a point to the left of 1, so maybe 0. F prime of 0. I'm going to have 5e to the 0, and then 1 minus 0. So I'm just going to get 5, right? That's just 5. I don't really care about the value. All I really care about is that that's greater than 0. So the function is increasing, right? It's increasing to the left of 1. And then let's test a point on the other side of 1. Let's try 2. And I'm going to get 5 e to the minus 2. And then I'm going to get 1 minus 2. Now I'm going to get, this is essentially 5 over e squared. But either way, that 5, I'll just write it as 5 e to the minus 2, and then times a negative 1, right? I don't really care what that value is, except that I know, e to any power is going to be positive. And I take that positive times a negative, I'm going to get something less than 0. All right, so that's telling me that it's decreasing on the other side of 1. All right, now the first derivative test tells me that we have a local maximum at that point. All right, so let me scroll down a little bit. So we get a local maximum when x is equal to 1. Now we're also asked for the y-coordinate as well. And so we need to go back up to the original function and find f of 1, right? We need to find f of 1 in order to find the y-coordinate that goes with this local maximum, right? We don't want to put it back in the derivative. We want to put it into the original function. So we're going to get 5 times 1. So we get 5 times 1, which is 5, and then e to the 1, or sorry, e to the minus 1, okay, which is 1 over e. So we essentially get 5 over e. All right, if I want the exact answer, that's the exact answer. Now I could, because I know I'm going to have to graph it eventually, it would probably be easier to graph if I have a decimal approximation of the y-coordinate. So if I put that in my calculator, I get 1.839. That's what I got when I put that in my calculator. So so I would need my calculator for this one, because I don't know what 5 over e is off the top of my head. All right. Now what about a local minimum? We only had one critical point and it was a maximum. So that means that there are no local minima. Okay. All right, so we've got we use this first derivative test to find the local maximum, and now we're asked to find the inflection points. And so inflection points, we're going to need the second derivative. All right, so even though we avoided the second derivative by using the first derivative test in part C. That was part B. Now we're going to need the second derivative. Now, let's see, I'm going to scroll. Do I have room? Yeah, okay, so the first derivative is up here. So I'm just going to scroll up so we can see the first derivative. We're going to take the derivative of that. And I think I'll use this this one here. Let me highlight it, what I'm going to use here. I'm going to use this one. Whoops, hang on. Didn't I get the okay. Meant to turn that on. Okay. So I'm going to use this one. I'm going to use that form and use the product rule again. So, goodness. All right, hang on. All right, I'm going to use the product rule now on that, and then I'll scroll up so I have some more room to work. All right. Okay, got the right thing. All right, so now, okay, so now I have 5e to the minus x times that thing in parentheses, 1 minus x. So I need to use a product rule again. So I take the derivative of the first, which is going to be a negative 5e to the minus x, and then times 1 minus x, and then plus the first, 5e to the minus x, times the derivative of the second, which is just going to be a minus 1. All right, now that we have that, I'm going to clean it up a little bit, because to find the inflection points, I have to set this equal to 0. And so I think I want to factor it. So let's put it over here. Okay, so I see there's a 5. I see there's an e to the minus x in both terms, right? I have two terms here. One of them is here and one of them is here, right? I have these two terms. And they both have and they also have a negative. So I'm going to factor out a negative 5 e to the minus x and then see what's left. All right, so when I do that here, I'm going to have 1 minus x left. And then when I factor out the negative 5e to the minus x, I'm going to have a plus 1 over here, right? So, all right, so let's see what that looks like. I can combine the 1 and the other 1, and I'll get minus 5 e to the minus x, and then 2 minus x. Okay? All right, now that's a lot easier. Now I can set that equal to 0 to find the candidates for inflection points. So I have a candidate for an inflection point at x equals 2. So remember this negative 5 e to the minus 5x, that can never be 0, just like we've talked about before. All right, now just because I have a candidate, that does not mean that that's an inflection point. I have to test it. So let's test it. We're going to test for a change in concavity, right? That's how we find an inflection point. We have the candidate, and we just want to test the concavity to the left and to the right of 2. So I'm going to use the second derivative. Let's pick 0. That's easy. That's to the left of 2. And I'll use the factored form. So I'm going to get minus 5 e to the 0 and then times 2 minus 0. So just 2. Now, that is just a negative 10 times e to the 0, which is 1. So it's just negative 10, which is less than 0, which means that it's concave down to the left of 2, right? And then let's test a point to the other side of 2, on the right of 2. So we could just pick 3, and we're going to get negative 5 e to the minus 3, and then we're going to have 2 minus 3, which is a negative 1. All right, so we have a negative times a negative. You're going to end up with a positive 5 e to the minus 3, right? But it doesn't matter. That's positive, right? Because e to the minus 3 is a positive number. This whole thing is greater than 0, so it's concave up to the right of 2. All right, so we can now verify that, yes, we do have an inflection point at x equals 2. And so now the x-coordinate is going to be 2, but we're going to end up graphing this. So we need to find the y-coordinate. So to do that, we're just going to find f at 2. So we're going to go back to the original function, right? We're going back all the way to the original function. 5 times 2e to the minus 2. So that is 10 over e squared. So I could write 10 over e squared. Now, because I have to graph it, I probably would like to have that as a decimal. So that's the same as 2 comma, what did I get? When I put it in my calculator, 10 divided by e squared gives me 1.353. Okay, so the decimal is just easier to graph. All right, so now the last step here is just to use the information that we have in the previous part, and we want to sketch a graph, an accurate graph of f of x. All right. So, so we had the first, in part A, we found the x and y intercepts, which happen to be both be 0, 0. So the graph has to pass through 0, 0. We had a local maximum at 1 comma 1.839. All right, so 1.839 is maybe about here. That was our local maximum. Okay, and then we had an inflection point at 2. The y-coordinate was 1.353, so let's say about there. And we also know that it's concave down everywhere to the left of 2. So this has to be concave down, right? Concave down to the left of 2. Now it probably continues on this way as well. But it's concave down. This is our inflection point. And then it's concave up on the other side of 2. It's always decreasing, but it never crosses the x-axis, right? Because there's no more x-intercepts. So what has to happen, if it's decreasing and concave up, it has to look something like that, right? It's concave up and decreasing, and it never crosses the x-axis, and it never increases either, right? Because we found in part, I think that was part B, when we tested for the local maximum, that it's always decreasing to the left of 1. All right, so that gives you a fairly accurate graph. We have the right concavity, we have the local maximum, we have the inflection point, we have the x and y intercepts. So we've got everything on there, and that's it. All right, so that is the last example, and I will see you in class.